A modern web app is far from a simple script tag. To ship code today, you run it through an industrial-scale pipeline. Before a single pixel renders for the user, tools known as bundlers and transpilers act as factory machines. This pipeline parses abstract syntax trees, maps out massive dependency webs, and cuts dead code before execution. But as codebases have swelled to millions of lines, the exact tools created to manage that scale have become the tightest bottleneck in the development cycle. The root of this bottleneck lies in an uncompromising architectural rule. JavaScript is strictly single-threaded. It can only execute one command at a time. JavaScript relies on an event loop. Small I/O tasks, like network requests, are routed to circular waiting areas, keeping the main execution path clear. But heavy CPU computations drop directly onto the single pathway, forcing every other packet to freeze. When you run modern build tools in a node environment, you force the system to swallow these massive CPU blocks. It has to chew through millions of lines of complex abstract syntax on a single thread. Relying on node-based tools to bundle today's massive web apps pushes the language past its physical limits. The single thread chokes, and local build times stretch from seconds into agonizing minutes. To bypass this wall, the industry is rewriting its core infrastructure using systems languages like Rust, C++, and Go. Unlike JavaScript, which requires an engine to interpret it on the fly, these languages compile directly down to native machine code. They execute commands with unfiltered, raw CPU power. This animated diagram illustrates their biggest advantage: multi-threaded programming. A massive parsing or bundling job is instantly sliced into equal chunks, and the workload is distributed across multiple CPU cores at the exact same time. By moving the build process out of Node and into a language like Rust, developers entirely bypass the JavaScript event loop. Changing the underlying physics of the process drops build times down to milliseconds. These powerful new threading workarounds have now moved beyond the developer's terminal and directly into the end user's web browser. Browsers now support WebAssembly, or Wasm, a low-level bytecode format designed to run alongside JavaScript natively inside the browser engine. When a web app needs to execute extreme computational tasks, like heavy cryptography or high-speed zlib data compression, it hands the complex math straight over to WebAssembly. This diagram shows how JavaScript also utilizes web workers to offload moderately intensive tasks, like real-time syntax highlighting, to background threads. The main UI track runs smoothly, while background threads process the heavy data safely out of the way. To ensure the interface never freezes, the modern web has physically separated visual rendering from heavy mathematical processing. This pivot towards systems languages does not mean JavaScript is dying or being replaced. Developers will continue to write their core application logic in JavaScript and TypeScript to leverage a massive open-source ecosystem and unmatched flexibility for building interfaces. JavaScript retains complete dominance over the I/O layer. It manages the user experience, manipulates the DOM, and routes asynchronous network requests. This image captures the new architecture perfectly: a vibrant, highly interactive surface layer powered by JavaScript, resting on a deep, rigid foundation of parallel metal pillars, where Rust and WebAssembly silently execute the heaviest computations. This division of labor gives engineers the highly expressive, dynamic experience of writing JavaScript, combined with the raw performance speeds of native compilation. The industry is now leaning heavily into brutalist systems languages, specifically to ensure they can keep writing JavaScript without grinding their pipelines to a halt. This separation of labor allows JavaScript to remain responsive at the surface, while underlying system languages process the heavy math, turning a single-threaded bottleneck into a concurrent architecture.